Hello everyone, welcome to lecture number 13. Again, I've divided this lecture into multiple parts, and we're going to do a lot of example problems as well in this lecture and in some of the next lecture as well. We're also starting a new chapter today. Interestingly, that is also chapter number 13. We finished the chapter number 12 last in the last lecture, and again in the last entire chapter, 2 weeks, we talked about what is Laplace transform, right? We solve so many integrals, we apply Laplace transform to the functions, to the operators. We also did one circuit example, but this chapter is all about circuits, and how to apply Laplace transform to the circuits and how to solve all of those circuits. So we're going to solve a lot of this RC, RL, RLC, natural step responses through Laplace transform, heavy-handed, in this chapter. Okay, so let's get started. In this part of this lecture, the A part, we are going to see how we can model the individual circuit elements, the resistor, inductor, and a capacitor in the S domain. Whenever we have to model an inductor, a resistor, or a capacitor in the S domain, right, we follow essentially three steps. And the process is, the very first step is that we start with writing the VI equation for that component, right? So for resistor, we know the VI equation is Ohm's law, which is V equals to IR. We know that for the inductor is, what is the VI relation for the inductor, right? Your voltage across the inductor, VL equals L di by dt, right? And similarly, what's the VI relation for the capacitor? We know that the capacitor current equals C dV by dt. So we start with writing these equations down, and then the second step is we are going to find the Laplace transform of this time domain equations. That's the second step. And the third step is we will construct a circuit out of those equations. So what I just said is going to become more clear in a second, because I'm going to apply this three-step process, starting with a resistor, then an inductor, and then a capacitor, right? Okay, another important thing before I go ahead and start modeling these circuit elements is the dimensions. In the S domain, the dimensions in the S domain for the voltage is volts second, for the current is ampere seconds, for the resistances S will be cancelled out, so the resistance or the impedance will remain ohms, right, or volts per ampere. And then for the so for the impedance is again ohms. For the admittance, it should be since admittance is the inverse of resistance, so it should be Siemens. So for the admittance it is Siemens, and for the impedance it is ohms. Voltage is volts seconds, and current is ampere seconds. Okay, so with that, let's start transforming our circuit elements now. Again, I'm going to start with the resistor. So very first step is we need to write the VI relationship of a resistor, which is V equals IR, or Ohm's law, right? So this is V equals IR. And we can model this V equals IR by this A figure, right? Over here you have a resistance R. This is a voltage across the resistance, and I is the current flowing through it, right? And R is a constant if you don't have a variable resistor, all right? So in this specific case, or even for a variable resistor, you can assume an instant where the resistance is constant. So for a constant resistance R, if you're going to apply a voltage V across it, you're going to have a current I flowing through it, right? And this is Ohm's law. So what we are going to do, ignore the B part. I'm going to talk about the B part in a second, right? So again, the first step is to write down the VI relationship. And the second step is to find the Laplace transform of that VI relationship, right? Now I have to apply Laplace transform to this thing. I know that the Laplace transform of the voltage should be capital V, and the Laplace transform the small current IA should be capital I. Laplace transform of I of t is capital I, right? So this is another point that I made in the last chapter, that the time domain signals, we usually express them with the smaller letters or denote them with the smaller letters, and the S domain signals, we usually write them with the capital letters. So this capital V is the S domain Laplace transform signature of the voltage, this V, and this capital I is the Laplace transform of this I, okay? Now, for example, if I were to apply Laplace transform to this equation, right? Laplace transform of V, right? R is constant, Laplace transform of R times I. R is constant, it should come out I. And so this is going to be I, capital I, and this is going to be capital V. So you just get the same Ohm's law back in the S domain, where R is a constant and your V and I transformed into Laplace domain, right? So for the time domain, right, so this is V of t, this is I of t. So you get capital I Laplace transformed current in the voltages, and you're going to get the Ohm's law kind of back. Now, interestingly, from this equation, now the third step is the first step again was writing the VI relation. Second was applying Laplace transform to that equation. And the third one is building a circuit. And from this equation now, we can see that our circuit can still be represented by a constant resistance R of R ohms, right? That will carry the current I, but this I will be ampere seconds, and the voltage across that resistance would be volt seconds, right? So again, we can easily represent this thing by this B circuit over here, right? Where you have a resistance R and the voltage capital V. This is volt seconds in the S domain, and the current I, ampere seconds flowing through the circuit. So the resistor remains the resistor, and your model is kind of a very simple, similarly looking model, only the V and I have been transformed into S domain. Okay, great. Right, so for the again for the resistor and the S domain, your time, once you transfer it to the time domain to the frequency domain, which is S domain, right? So that should not change your resistance element or the resistance R over here. Let's see what is going to happen in an inductor in the S domain as well. I'm going to use this, yeah. Okay, so inductor in the S domain. I am going to start with showing you what an inductor in the time domain circuit looks like for an inductor, right? So this is a time domain representation of an inductor, where we have an inductor of L henries, right? So this is the inductance, L henries. And I'm going to assume that it has some initial energy stored, right? And then at the end of the day, I'm going to show you what the circuit or what the entire thing is going to look like without initial energy stored. But let us start with some initial energy stored. If there is some initial energy stored, so there is an initial condition which is I naught, and so there must be some initial current to the inductor, right? That is represented by I naught over here. Okay. And then this V represents the voltage across the inductor, and this I represents the current flowing through the inductor. Okay, so this is nice. I started with this. So my first step again is, as I have told you, that we need to start writing the VI relation of the circuit element, which is an inductor. And that VI relation I already told you, right? The voltage across the inductor is L di by dt. So I'm going to write that equation down now, which is over here, right? So V equals L di by dt. Now what I am going to do in the second step is, after writing the VI relation, we are going to find the Laplace transform of this equation, right? So let's find the Laplace transform of this equation, and here is this thing, right? So for example, the Laplace transform of a derivative of a function equals to as f of s minus f of 0 negative, right? So I'm using this identity. So we can apply exactly the same thing over here. So for example, right, so you can take a Laplace transform of V of t should be equals to L is a constant times di by dt. So it should be s times I of s minus I of 0 negative, right? So this comes out to be capital V. This should be L times Si minus I naught. This is the initial condition of the inductor. So I can write it with a capital I. So L Si minus, sorry, I naught. L times I naught. So this is going to come out to be your Laplace transformed equation. You start with the VI equation, finding the Laplace transform, right? Which is, again, coming out of it to be this thing. So all we did was we applied the Laplace transform on this equation that I just did over here by using this identity. Okay, so once you do that, okay, nice. Now, if you look closely, and I'm going to show I'm going to build two different models of an inductor in the S domain, right? So let's start with the first model. Again, step number 3 is making a circuit model based on the equations, Laplace transform equations that we got. On the left hand side, I have a voltage, right? On the right hand side, I'm gonna have voltage representations and how I am saying that, right? So for example, this is V, and here is your current I. So this capital current I was a S domain transformed signature of I of t, which was a time domain, time varying current I, right? And this I naught is a constant I naught. So I can practically write this thing with kind of a combination of the two things, right? So the first one is this VI relationship, or kind of an Ohm's law, where you have the voltage, right? So where you have V equals SLI, right? Let's call it V1, and let's call V2 as minus LI naught. And practically your V over here is the summation of the two. So I can practically use my Kirchhoff's voltage law and write this thing down or make an equivalent circuit, right? This is a kind of a combination of the two different voltages, where the first one is you have a current I flowing through this element, and SL would be the impedance of this thing, right? And again, since V equals to IZ in this case, so Z should be equals to SL. So again, one of the circuit configuration that can come out of this equation is your impedance can be SL ohms for the inductance, and the current I is going to flow through it. And then you're going to have in series this L times I naught independent voltage source connected to it. And this is a constant voltage source because I naught is constant here, initial inductor current, I naught value. So I can convert this equation again into a circuit, which is going to look something like this. Now, if you look closely over here, right, this is your impedance, which is ZL. And you have an I current flowing through it and a voltage across it. And this is the total voltage across it, right? So this voltage was V1 and this voltage was V2. And we are combining this V1 and V2 over here. And again, this minus Li naught. So why you have this thing negative and the positive, right? Because you are adding minus Li naught to this inductor impedance over here, SL. So this is how you can make a kind of a series model of this Laplace transformed circuit element. We can have another kind of a circuit representation in the S domain for the inductor, and how we can find that out by solving the same equation, this equation, solving it for the current, right? I have two variables here. One is the V, other one is the I, which were initially time varying variables that I converted into S domain. So if I will solve this equation with respect to the current I, what I'm going to get is practically this, right? So I can solve this, if you want, as V plus Li naught over SL equals capital I, right? Again, this equation. Yeah. So I equals V plus Li naught over SL, and then you can further divide this. V over SL and I naught over S, because L will be cancelled out. Now, if you look at this equation, right, this is also kind of an interesting equation. But if you look at this equation, I can potentially model this equation into another interesting circuit, where I can have two parallel branches, right? This is the total current, and these two things also represents currents in two different branches. And you can just imagine that you have a total current with one branch, something in this branch, and another thing is in branch connecting to it. And I'm going to make a kind of a similar circuit to this thing. Now, what is over here and what is over here, right? So for example, if this was I, right? So for example, on the left hand branch, you can have V over SL. What is V over SL? I can model it as I equals V over Z, right? So Z again, ZL is SL. So I can still have a kind of a inductance impedance, ZL over here, right? And my current will be divided, and the voltage across this will be V. And on the other hand, I am on the right hand branch, I am going to have another constant current source, which is going to come out to be I naught over S. So, and this is what I just said, right? So the S domain circuit satisfies this equation with an impedance of SL ohms, which is connected in parallel with the independent current source of I naught over S ampere second, right? Which was this. And the circuit is going to look something like this as I have drawn, right? So this was your total current. It gets divided into, right? Again, you can see from here, this was your equation, into two parts, V over SL, I naught over S, right? Okay, so this was your current I that gets divided into this part, SL, right? So I can model this as the voltage divided by the impedance plus the current that is going to flow over here plus the current that is flowing over here, I naught over S. So again, I ended up making another model of a circuit. So we can transform the resistor into only one model, but the inductor, and we're going to realize the capacitor as well, into two different models, a series model and a parallel model, depending on how we transform the equation. Okay, so the last thing to talk about over here is that, again, in both of these models, we assume that there was an initial energy stored, I naught, which shows an initial current. However, if there was no initial energy stored, this means that I naught is going to be 0. If I naught is going to be 0, then our circuit is going to be very simple, and both the models will reduce to the same thing. If I naught is 0, this right branch is going to go down, right? Similarly, in this case as well, there is not going to be anything Li naught. So all I will be left with is just a inductor representing the impedance of the inductor, right? So my model will be reduced to this simple model where I'm going to have an I current flowing through it, voltage across it, and the impedance of this, right, of the inductor, which is SL. Again, this simplified model is when your initial current is 0 or there is no initial energy stored. So understanding that which model to use when is useful. And we're gonna do a few example problems where you're gonna realize that when to use a series model, when to use a parallel model, and when to use a reduced model. Again, in a reduced model, your energy is 0. And then when to use a series and a parallel model depending on what sort of the circuits you're solving. So we're gonna do some examples to understand that. Okay, let's very quickly do the capacitor as well. And the modeling of the capacitor is very similar to the modeling of a inductor. We're going to follow exactly the same steps. So I'm going to start with the capacitor, and again I'm going to say that there was some initial energy stored in the S domain. So there was initial energy stored in the capacitor, right, which was V naught. So there was an initial capacitor voltage, and since there was an initial energy stored, right, as we have seen in the inductor, we ended up getting two different models. And similarly, we're going to realize that we're going to get two different models or circuits for the capacitor as well. So let's draw the time domain circuit. So here's a time domain circuit, or the model of a capacitor, where you have the initial capacitor voltage V naught, right? Again, we know that this is constant. Here's the capacitance in farads. The voltage across the capacitor is V, and the current is I. Now the second step, as we know, is or the first step, as we know, is finding the VI relationship. So what is the capacitor voltage? What is the VI relation of the capacitor? We know the IC should be equal C dV by dt, right? So the capacitor current is equals to C dV by dt. And now we can just simply take a Laplace transform of this equation as a second step. So Laplace transform of I should be equals to C because C is a constant, I can take it out, right? Laplace transform of dV by dt. So this would definitely be equals to C times Laplace transform of dV by dt should be S times V minus V0 negative. So CSV minus, and this is the initial condition V naught, times C. Okay, and this is I. Okay. So interestingly, right, so if I'm going to take a Laplace transform of this equation, capacitor current, I'm going to get this equation, right? So let's do the second step as well. So I got this equation. Now the third step again is I need to make a circuit. Since this is I got the current out, right? Again, I'm going to do exactly the same thing. I'm going to model it two ways, right? Once I'm going to write the equation in terms of the current, and in another way I'm going to write the equation in terms of the voltage. So that we initially got the current. So yeah, so you can look over here at this equation and you can realize that this current I is composed of these two currents, right? So I can potentially model it again in form of the two branches. So in one of the branch, right, I'm gonna have an admittance of CS or the impedance of 1 over SC because I equals V over Z, right? And in the other branch, I'm gonna have a constant current of CV naught in the opposite direction or in the direction that will add to this I. Okay, sounds good, right? So this is what I just said, right? And this is going to become more clear as well when I'm going to draw a circuit. So the circuit again is this capital I is composed of two things. One is here, the other one is here. This CV naught is a constant current, right? And this represents your kind of a time varying because your V, capital V and the capital I were time varying I and the V in the time domain that got transformed into the Laplace domain. So these are in over here, these are I of S and V of S, if you will. And CV naught is a constant thing. So I can potentially again model it as two separate branches, right? So again, this is your current I that gets divided into two parts. The first part is SCV, right? Again, your I is equals to SCV, I1, let's call it I1. And again, I know that it should be equals to V over Z, C. So ZC is 1 over SC. So that is why you got your impedance over here of the capacitor is 1 over SC. And similarly, the other branch has a constant current of minus CV naught, right? So you get CV naught flowing into the direction that is adding to the current I. You can just assume a simple Kirchhoff's current law over here, or Kirchhoff's current law over here. And this is what we just kind of talked about over here. You have two branches. The first branch has an admittance of SC or impedance of 1 over SC, and the second branch has an independent current source of CV naught. So this is one of the circuit representation that you get. Now you can find the second circuit representation as well. And in order to find the second circuit representation, you know that you have to solve this equation or this equation for capital V. And you can easily solve it. I can potentially solve it as well. Right? I plus CV naught, I can take this CV naught on the other side. I plus CV naught divided by CS. Why did I do it? Okay, so I plus CV naught equals to CSV. So I can do CSV, SCV, and cap. Okay, so this is I got. No, so sorry, just says CS. CV naught and SC. Yeah, so the V is over here, so there shouldn't be a V. So it should be I over CS plus V naught over S. Okay. So here's the second equation that I got, and I'm going to show you in a second as well over here. So the voltage over here is equals to the current I times again V equals to IR, right? You can call this V1, right? So now you can, for example, apply Kirchhoff's voltage law, where this voltage is composed of V1 plus V2, if you will. And the V1 is I times Z, right? So your again Z is going to be 1 over SC plus V2 is V naught over S. So this kind of circuit shows that you can have a combination of the two voltages here, V1 plus V2, where V2 is an independent voltage source, V naught over S, and your V1 is essentially the voltage across the capacitor, which has an impedance of 1 over SC. Okay, so this is how you can represent this in a kind of a series model, right? So again, this is a voltage that was a combination of this voltage and this voltage, V1 and V2. And this voltage was simply V naught over S, and this voltage was the impedance times the current that was flowing through it. And yeah, this is what I just said. So again, in short, we can model the capacitor as well in form of a series model and a parallel model. In both of these cases, if you realize it, if I'm going to take the initial energy out, V naught out, both of these models, this circuit and this circuit, will reduce to only one element, or will be simplified into a simple representation of 1 over SC. Or this equation and this equation will be only be composed of this one component, right? Which is a simple Ohm's law, if you will. V equals I times Z, where Z is represents the impedance of the capacitance, 1 over SC. So once you're going to take the initial voltage on the capacitor is 0 because no initial energy stored, right? The circuits will be reduced to this, where you're going to have a simple V equals I times ZC, and ZC is 1 over SC. So depending on, again, which model to use and whether there's initial energy stored or not, you can pick different circuits to choose. Okay, here's kind of a summary of what we talked about in terms of, again, finding these models out. We started with a circuit element. We write down its VI relationship. Then we find a Laplace transform of that, and then we constructed a model. Okay, so in case of a resistor, it was a very simple, similar thing. Resistance was constant, and V and I just got transformed into the Laplace transformed. The relationship of for both inductor and the capacitor has a derivative. So we found the Laplace transform of that derivative. And once we found the Laplace transform of that VI relationship, in that case the derivative, we found these equations, and then we model these equations. For example, this equation can be modeled as a summation of the two voltages, SLI and LI naught. That is why you got a series circuit. And this equation can be modeled as a summation of the two currents, V over SL and I naught over S. So this is what you got, right? And similarly, we did the same thing for the capacitor as well. So the point is, the resistance is a simple resistance in the S domain, or the circuit model is simple. The inductance and the capacitance gets transformed into a series or a parallel model depending on which equation you pick. However, if there is no energy stored, right, then your model becomes very simple and just over here like this, right? And again, this assumes that 1 over, this is SL, and the impedance of the capacitor is 1 over SC. And again, if you were to take this, 1 over ZL, and V is I times ZC. Okay, so starting in the next lecture, we're going to start using these circuit models, and we're going to start solving some of these circuits as well. So I'm going to talk to you in the next lecture. So with that, thank you so much. Have a good rest of the day. Thanks. Bye.